Hi, so this is the second lecture for the probability course. On Monday, we're going to have an interactive lecture on Zoom, which you can access through Canvas. We'll discuss a variety of things. I encourage you to log on in real time if you can, so you can ask questions and get the feel of what the interactive lectures are for. Usually the interactive lectures will be supposed to go over the homework, but because we haven't had homework yet, it'll be a little more general. Anyways, the first thing I want to talk about today is to follow up on something I didn't quite have time to finish at the end of the last lecture, which is this thing about binomial coefficients. So if we try and recall the logical thread of what we were doing before, we had this principle of successive experiment, which said that if you have one experiment with n outcomes and another experiment with m outcomes, then the total number of outcomes for the two experiments is n times m. So you take the product of the individual numbers of outcomes. And so that was the first thing we thought, and then we used that to derive n factorial as the number of ways to arrange n distinct objects in a line. And then from the concept of n factorial arranging distinct objects in a line, we arrived at a concept of multinomial coefficients for arranging a group of colored spheres in a line. The point being that the spheres with the same color are indistinguishable, but spheres with different colors are distinguishable. And as a special case of that, we found these binomial coefficients, which count the number of ways to arrange k red spheres and n minus k green spheres in a line. And so physical analogies are fundamental to understanding probability, and we're going to enrich the physical analogy of arranging red and green spheres in a line by saying just that, well, we're going to put them in boxes. So we have this line of boxes, n boxes, and then we're going to put these green and red spheres in them. And so there's an interpretation which is obvious if you just shift your perspective a little bit, which is that the number of ways to arrange k red spheres and n minus k green spheres in a line of boxes is exactly the same thing of the number of ways to choose k special boxes from the total of n. And the connection is you just say a box is special if it contains a red sphere. So I'm offering you highly specific physical analogies like red and green spheres because I firmly believe that fixing as specific a physical analogy as you can for each probabilistic concept is important, because it helps you memorize and build the logical structure in your head as you're learning it the first time. But hopefully you can see on an intuitive level that the words red and green are just placeholders here, and everything would be identical if I were talking about red spheres and blue spheres. Okay, so for this reason, binomial coefficients are often referred to simply as n choose k, because it's the number of ways to choose k special things from a total of n things. So let's look at an example which puts together some of these concepts we've been discussing. So let's read what we have here. A committee of 3 pigs is to be chosen from a group of 20 pigs. Another committee of 2 cats is to be formed from a group of 5 cats. A specific pig and cat do not like each other and will not serve together. How many committees can be formed? Okay, so this is an example of the basic paradigm for doing problems in a probability math course, and on a higher level, coming up with probabilistic models for real-world data and using mathematics to come to interesting conclusions. So what we're doing is we have a bunch of words with various numerical data embedded in them, and we need to figure out how to arrange all of that data into a specific mathematical formula that ends up just being a bunch of numbers added and multiplied at some level. And so what we're always going to be doing is trying to reduce things to a form where we can outsource the work to a computer. And obviously, you've had experience with calculators for adding and multiplying. You probably have an intuition that a calculator is just a very stupid computer. And one of the things we're going to do in Monday's lecture is discuss a freely available online interface for a very sophisticated artificial intelligence system that you can use to help you do math. And the basic principle in this course is that I want you to use this system I'll show on Monday as much as possible to make your life easier, and also to reduce the chance you make mistakes. So I'll tell you what kind of things you can plug into this system, and it will understand. And when one of the things it can understand is a binomial coefficient. So what I'm going to do is I'm not going to write any explicit calculations until the very end. I'm just going to set everything up in terms of binomial coefficients and then write the final answer I get at the end, which can be just typing some stuff into a computer and pressing enter. Okay, so let's think. A committee of 3 pigs is to be chosen from a group of 20 pigs. Okay, so we can immediately clue on to the word, okay, we're talking about something being chosen. So this is a binomial coefficient. It's 20 choose 3, choosing 3 pigs from 20. And the same thing, we're choosing 2 cats from a group of 5, so that's 5 choose 2. And then the principle of successive experiments tell us that to do the pig choice and then the cat choice, we multiply them. So before we look at this particular unfriendly relationship between a specific pig and cat, there's 20 choose 3 times 5 choose 2 committees that you could possibly form. But now we need to take into account this issue it describes, where a specific pig and cat have some kind of tremendous hatred for each other and refuse to serve. So how many committees are excluded by their bad relationship? Well, how many committees have the unfriendly pig on them? Or how many pig choices include the unfriendly pig? Well, if we automatically include the unfriendly pig, there's 2 spots left and 19 friendly pigs to fill them. So that means there's 19 choose 2 pig committees, including the unfriendly one. And if we automatically include the unfriendly cat, there's 4 friendly cats left to fill the other spot on the committee of 2 cats. So
there's 19 choose 2 times 4 choose 1 committees where the unfriendly pig and unfriendly cat would be forced to serve with each other. So we subtract those and can type this into the software I'll show you on Monday, which is called Wolfram Alpha.
Oh, as a matter of fact, I did type this into Wolfram Alpha, and the point I'm making about typing this into Wolfram Alpha as opposed to trying to do factorials yourself with a calculator is not only is it easier, but it reduces the chance of error. And so gave me 10,716, and as a human being in 2021, I know better than to argue with the computer about arithmetic, and I certainly don't feel like doing this in my head, so I just got that as the answer. So if you look at what we did here, to take the numbers 3, 20, 2, and 5 and get from that the number 10,716 is obviously not something you can just do unless you have the intellectual structure of what we've built to interpret this word problem with these particular mathematical formulas. So that's all I really am going to say about the binomial coefficients. That was a hangover from the last lecture, and now we'll go on to start talking about the main topic of this course, which is the axioms of probability.
So the way to think of the axioms of probability is that it's a intellectual structure which formalizes a bunch of very natural real-world phenomena that have to do with the idea of chance or randomness or even uncertainty. And the way it does this is by, first of all, attaching very specific definitions to certain words that we're going to use consistently. And so the first definition that we're going to make is the definition of a sample space. And so the symbol we'll usually use for a sample space is this capital omega. And so the sample space is the set of all possible outcomes to an experiment. And so it's just everything that can possibly happen within the experiment you're considering, or everything that you could possibly observe as a result of the uncertain phenomenon you're trying to predict. And so the physical analogy you always want to go to as the first example of a probabilistic experiment is coin flipping. So if we flip one coin, the sample space has size 2. There's 2 outcomes where we have heads or tails. And okay, so that's a small sample space for the simplest of all probabilistic experiments. We can think of a slightly more complicated experiment where we flip 2 coins. In that case, we have an outcome where they're both heads, where first is heads, second is tails, first is tails, second is heads, or both are tails. And so this experiment has 4 possible outcomes. And we can see a particular manifestation of the principle of successive experiments here, in that if you think of the flipping 2 coins thing as flipping 1 coin and then flipping another coin, you should expect that 2 times 2 is 4, which is something we can think of as an extremely simple example of verification that our theoretical structure is plausible. We're building more and more into it, and what we've introduced here with the idea of a sample space as the set of all possible outcomes conforms with what we were thinking about before with counting numbers of outcomes in terms of the principle of successive experiment. All right, so the idea of a sample space doesn't really have anything mathematical in it. It's more just a list. If you were thinking about it in terms of computer science, you would think about it as like a character string or a sequence of character strings or something like that, or a sequence of images, but the sample space itself doesn't have very much mathematical structure. It's just a set of possible outcomes. Okay. So the next word we want to define and the next concept we want to formalize in our probabilistic modeling structure is the concept of an event. So the way we want to think of an event is that it's a set of particular outcomes with a common property. So if we're sticking with our flip two coins as an example of a probabilistic experiment, we can think, all right, an event could be at least one tails. So another way of phrasing that would be to say that we're looking at the event that we see at least one tails. That's something that can potentially happen as a consequence of our experiment. So an event is a set of outcomes that are defined by some common properties. So here we have a sample space with 4 outcomes, and an event is a subset of that. The event being described on this example is heads, tails, heads, and tails, tails. It's a set of 3 outcomes within a larger sample space that contains 4 possible outcomes. There's this one outcome, heads, heads, which is a possible outcome of the experiment, but is not in the event we're considering, or because it doesn't have the property that defines the event, where we look to see at least one tails. So sample spaces are, at some level, the logical foundation of probability, and events are just subsets of sample spaces, but events are vastly more important in probability than sample spaces, and listing out an entire sample space is rarely a useful approach to solving a probabilistic problem. It's like, usually the way to think about listing out every element of a possible sample space is that this gives you such a gigantic quantity of information that the real task of probability is to analyze this data and learn something useful from it. And an event is kind of the first conceptual step towards doing that. And you may have a vague awareness that probability is the mathematical side of a science called statistics, which is exactly doing this, taking gigantic quantities of data that are too large to understand looking at one by one, and using the math we're going to talk about in this course to make predictions about large-scale phenomena that may arise as a result of these data in this experiment. So events are much more important than sample spaces, so we'll commonly use letters like A or B or C for events. We may list them out like A1, A2, A3, like that. So you should expect to see events come up all the time as kind of the most essential mathematical object we're going to be talking about in this course. So in terms of remembering symbols, the sample space is just the set of all possible outcomes. It's everything that can possibly happen, and we'll really only ever see this capital Omega symbol for that. On the other hand, events will be using capital Latin letters, and we'll be seeing all kinds of different events all the time. All right. So the next concept we want to define is the conjunction of events. So if we have two events, A and B, the conjunction is a third event that happens when both of the two constituent event happens. The conjunction is the event that A and B happen. So we denote it with this little infix wedge symbol. And if you've studied computer science at all, or maybe even just done some programming, you may have seen this symbol before as a Boolean operator for logical and it's playing exactly the same role here. You can think of A and B as conditions which may or may not be satisfied, and you know, A is an event that something happens. It's a property that could be satisfied by an outcome of an event. It's a condition that you can place on an observation. So it's like you're observing something and you have a piece of data and you're placing a condition on this data and saying, does this condition apply or not? And what we're doing with the conjunction of events is we're saying, all right, I'm going to create myself a new condition where I say that the new condition is satisfied when both of the constituent conditions are satisfied. And that's the conjunction of events in probability theory. Another way this same concept manifests itself is as the concept of intersection in set theory. The intersection, if you're thinking about events as subsets of the sample space, the conjunction is the intersection of the two subsets. So we can see an explicit example with what we're doing in our two coin flip. So let's say that A is an event where we're saying the outcome has at least one heads. So there's 3 of our 4 outcomes which fall into that category. Heads, 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 tails, and tails, heads. So those are the ones we've marked green. And then we can say, all right, so B is the event that we see at least one tails. So that's a condition we're placing on our data, and we can see which entries in our database satisfy that. We can see it's heads, tails, tails, heads, and tails, tails. So those 3 outcomes are in the event B. And then the conjunction of the 2 events is what we get by looking at the outcomes with both a green dot and a blue dot. Those outcomes where the two conditions defining the two events are satisfied together. And so those are the ones we've marked orange. And you can see it's pretty obvious that the conjunction is always somehow contained within the two constituent events. It's maybe the same size as them, but it can never be larger. The conjunction is always smaller than the two constituent events. The way we're going to interpret that later on is by saying the conjunction can never be more probable than the two constituent events. Okay, so this next page is very similar to the previous page. To be honest, when I wrote this page, I copied and pasted the previous page and then erased and changed certain small pieces. And if you want to, one way to study this lecture would be to look at this page and the previous page in the notes and see exactly which words I changed. But I changed conjunction to disjunction. So now we're defining a new concept called the disjunction of events, and we're saying that the disjunction is the event that, oops, I overcopied. Let's see here, better rewrite this. Okay, so the disjunction is the event that at least one of A or B happens. And we denote it with this little V symbol, which you may have also seen in the same context of Boolean logic, which is the foundation of computer science. And so what we're saying is that this is the event that at least one of the constituent conditions are satisfied. So if we're looking at what we're saying here with our two coin flip example, we want to see everything that has at least one heads or at least one tails. And so what happens there is that it ends up every possible outcome is in the disjunction of these two events. Because if you flip two coins, then, well, you're going to see at least one heads or you're going to see at least one tails. So that's just something that can happen. It doesn't always happen, but sometimes the disjunction of two events is certain. In this case, it is. All right. So the next concept we want to introduce is what we're going to call the complement of an event. So the complement of an event is just the event that it does not happen. In Boolean logic, this would be the not operator. And so we're going to denote it by putting this bar over the event. And so you figure out the complement of an event just by looking for everything where its defining condition or property is not satisfied. So in our double coin flip example, we can say, all right, if A is the event that we see at least one tails, what's the negation of that? What's the case where that doesn't happen? Well, the only way you can fail to see at least one heads is if you see two tails. And so we've marked that B is the complement of A. It's the event that none of the outcomes in A happen. All right. So this isn't really anything conceptually new. It's just saying that we're going to look at the disjunction and conjunction operators the same way we look at the plus operator and the multiplication operator, in that, okay, so here I'm introducing the disjunction symbol as a binary connective. I'm saying that we're looking at the disjunction of two events. And then you may or may not remember if anybody ever introduced the addition symbol to you. I don't remember who first introduced the addition symbol to me, but it would have been introduced to you with two numbers, one on each side. And so, at some point later on, you would have figured out that it makes sense to add up a whole list of numbers. And that's exactly what's happening here. You can just say, I'm going to take multiple conjunctions and multiple disjunctions. You have to be much more careful with mixing up conjunctions and disjunctions. If you want to create a logical statement which mixes up conjunctions and disjunctions, you need to parentheses to parse it better. But just like with the way you need to put parentheses if you mix up addition and multiplication, and there is a setting, it's very, very abstract, but you can interpret conjunction and disjunction as a form of addition and multiplication. So the thing we're saying here is that we're just going to say, yeah, if we use the ellipsis for a long disjunction, we're meaning we say A1 or A2 or A3 up to or AN, and we may do it with a big symbol and a counter for the counter variable for the loop that we're running, or however you want to think of this symbol K that's indexing the events when we use the large prefix. Okay, so the last concept we need to get to before we state the actual axioms is the concept of mutually exclusive events. So we say that two events are mutually exclusive if their conjunction is impossible. So, we have these two events, and they're each defined by some property or condition, and there's just no outcomes that share both properties. There's no outcomes you can find which satisfy both conditions. And so this is an extremely special relationship between events when their conjunction is impossible, and we have a special phrase for it. We refer to it as being mutually exclusive, and if you think about the way you may have heard the phrase mutually exclusive in ordinary life, that hopefully should conform with your intuition. So the way we're going to denote this symbolically is by saying that A conjunction B is equal to this little upside down T thing, which is a common symbol for logical impossibility or contradiction or falsehood. So it's like saying that A and B equals impossible. That's what the symbolic notation in the orange at the bottom is saying. Okay, so now that we have the construction of events within sample spaces, we can introduce the real mathematical content of the formalism we're describing. This is what's called a probability function. So a probability function assigns a real number to every event in a sample space. So it allows us to answer the question, what's the likelihood that this event happens with a real number. That's the way you should think of a probability function. It's some kind of mechanism which takes an event, any event you want in a sample space, as input to the question, what's the probability this event happens? And it outputs a mathematical answer to that question, which is a real number. And there are certain rules to how real numbers answering questions about the probability of events conform to the concepts we previously discussed. So these are stipulated by 3 axioms for probability. So the first axiom for probability is the stipulation that the probability of an event can't just be any real number. It has to be a real number between 0 and 1. And if you think about the way you've thought about probability or chance or luck in your life before, you've probably discussed it as saying, like, oh, I read Joe Biden has a 63% chance of winning the election or something like that. And this intellectual paradigm whereby people discuss probabilities as percentages is, to a mathematician, a little bit weird that everybody's focused on the number 100. That's obviously an artifact of the fact we are great apes with 10 fingers. And so rather than picking the number 100 as our basic scale for measuring likelihood or probability, we're going to make a choice more amenable to the mind of an abstract mathematical entity which doesn't have 10 fingers. And we're going to say that we're scaling everything to be between 0 and 1, because 1 is just a really fantastic number. Mathematicians love the number 1. So, informally, the way to remember the unit interval is probabilities are percentages, with the small caveat that mathematicians don't believe in privileging the number 10, so we scale everything to 1. So the second axiom for probability is that the whole sample space certainly counts as an event. You can think of it as the event that whatever tautological or self-evident property happens you want. If you're flipping a coin, the most obvious way to think of the sample space as an event is just to say, okay, the sample space is the event of heads or tails. It's the disjunction of the two obvious possibilities. But anyways, the sample space is a fair example of an event. It's a subset of itself, and so we can plug the sample space itself into the probability function and ask it, what's the likelihood of the whole sample space? And the axiom of certainty says, well, the likelihood of the whole sample space is 1, because when we defined the sample space, we said that it contained all the possible outcomes. So literally by the hypothesis in our intellectual formalism, we've forced ourselves to acknowledge this axiom that the sample space contains all the events, and so something has to happen. That's doesn't make sense if you do an experiment and you just say, oh, nothing happened. Something has to happen. So we're saying that the probability of something happening is 1. There's 100% chance that some outcome occurs. Okay. So those are the first 2 axioms for probability, and they're pretty close to the surface. But this axiom for mutually exclusive events is much deeper and represents the real kind of epistemological engine that makes the formalism of probability that we're learning in this course so powerful. And so the third axiom we're discussing here is what we're going to call the additivity axiom for mutually exclusive events. And so what this is that if you have a list of mutually exclusive events, you can calculate the probability of their joint conjunction, their joint disjunction, by just adding up the individual probabilities. And the reason this is what allows the mathematics of probability to happen is because this is the way you turn Boolean logic into addition and multiplication of real numbers. And, at the highest level, math is just trying to help out the world with using numbers to describe stuff. And what we're doing here is stipulating a very profound principle that humans arrived at over many centuries of studying chance and randomness in empirical phenomena. And, the reason, honestly, I think the best way to approach this is to say that the motivation is simply too deep to phrase in a single sentence. To understand why this is a good axiom, you really need to see it used in probability several times. And, this would be a point where you really just have to bite the philosophical bullet and say, I'm going to make this hypothesis and just carry it forward. One thing I could try to say to motivate why this is a good axiom is that if you're looking at a sample space, which let's call our sample space omega, and then you have 2 events which we're thinking of as subsets of our sample space. And so the 2 events as subsets of the sample space being mutually exclusive, that just means in our picture we should draw them as non-overlapping. And if you think about the concept of area as you see it in my 2-dimensional plane here, it's hopefully clear that if A and B do not overlap, then the area of them put together is the sum of the individual areas. Whereas if A and B do overlap, then the area of them put together is smaller than the sum of the 2 individual areas. So what's going on with this additivity axiom is a very, very high level analogy between the concept of probability and the concept of area. And the reason we think it's a good idea to say that this is how probability functions behave is because if you study probability at a graduate school level, you'll find that ultimately it is constructed based on the way mathematicians give a rigorous definition to the concept of area. All right, but as I said, area as an analogy for probability is an extremely high level thing that's very hard to carry forward in the subject, and I don't especially recommend that as something you try and use to understand things. It is there at a very, very deep level, but it's not an especially useful thing for a first course in probability to emphasize. I just brought it up here because it gives you some idea of where this axiom is coming from. All right, so we can see an example of how to just do a straightforward manipulation with the axioms of probability. So let's say we have an event and we're asked to figure out what's the event of the complement in terms of what's the probability of the complement in terms of the probability of the original event. So it's just asking you, give me a formula to figure out the probability that something doesn't happen, assuming I know the probability it does happen. Okay, so let's think about how we can do this. So one thing that's straightforward to observe is that A and A complement are mutually exclusive. It's impossible that something happens and doesn't happen. That's inherent in the logical construction of the concept of a complement, that it's mutually exclusive with the original event. The complement is defined as being not the original event. So since we know A and A complement are mutually exclusive, they can't both happen, we can apply the third axiom of additivity to say that the probability of the disjunction of A and A complement is the sum of the two individual probabilities. So again, I emphasize, it is absolutely illegal to write this equation if you don't know that the two events are mutually exclusive. The reason I'm allowed to write this equation is because if I go back to my axioms of probability, it says that I can do this for mutually exclusive events. If you don't know that the events are mutually exclusive, you're not allowed to just suddenly start turning disjunctions into plus symbols. But here we know that these events are mutually exclusive, so I'm allowed to turn this disjunction into a plus symbol. And then the next thing we can observe is that the disjunction of A and A complement is certain. It's like, well, either something happens or it doesn't happen. And another way of saying that is that the disjunction of A and A complement is the entire sample space. If we want to see that on a low-level data point for data point level, we can look at the example we had in the definition of the word complement. It's like, okay, when you write it out like this, it's really obvious the two things we said in that example we're doing now, that A and A complement are mutually exclusive, there's nothing that overlaps, and together they fill out the whole sample space. Their disjunction is certain and their conjunction is impossible. So since the disjunction is certain, we know that it has probability 1. And then we can just do elementary rearrangement to get the formula that we're asked for in the question. We just say the probability of A complement is 1 minus the probability of A. And so, on a, if you wanted to, so, you can think of this formula as something you know on a mathematical level about probabilities. And if you were thinking of how you would explain this in ordinary life, it would be like saying, well, okay, so if there's a 40% chance it rains tomorrow, what's the chance it doesn't rain tomorrow? Well, what do? You do 100 minus 40. And all we're doing here is just formally deducing that principle from the axioms of probability. We're saying that if you want to figure out the probability that something doesn't happen, you take the probability of certainty, which is 1, and subtract the probability that it happens. Okay, so as I said, Monday's lecture will be interactive on Zoom, which you can access through Canvas, and I encourage you to come, even if you don't plan to come consistently to the Monday lectures, just so you can see what happens in the first one. All right.